Good evening and welcome to GMAETS 41's YouTube channel. In our physics class today, I'll be teaching you vectors in 2 dimensions. You will recall that in our previous class, we learned about vectors in 1 dimension, how to resolve such vectors. When you have vectors in 1 dimension, what you expected to do. After defining the resultant of a vector, I explained that if a vector is in 1 dimension, that is a line, which could either be that the vector is moving eastward, which is right direction, or westward, which is left direction, or the vector is moving upward, which is north, or downward, which is south. Explain that all you have to do is simple. Carry out algebraic summation of the vectors. Add them. Simply what? Add them, respecting their signs. Because in such a case, it is possible that a vector might be assigned positive value and another vector might be assigned negative value, especially if they are moving in opposite direction. So in this class, we're going to give attention to another dimension of vector, which is vectors in 2 dimensions. How do you resolve such vectors? So once again, welcome to our class. I hope that the network allows us to do the needful. Once you join the class, please immediately give this live class a like it, and then share the link to your friends so that they can also join. Is that okay? Share the link to your friends so they can also what? Join. So let us get to business. When you are dealing with vectors in 2 dimensions, you recall that in our previous class, I explained that such vectors can be represented in a plane. The plane here is the rectangular plane. Take note, the plane here is what? The rectangular plane. So what am I saying? When a vector is in 2 dimensions, that vector can be represented, all right, in a plane. You use a plane to kind of locate the position of the vector. This network has started hanging here, but I just hope it is okay at your end. You can see what it is doing here. I just hope it is okay at your end. Okay. All right. So when we say that the vector can be represented in plane, this is simply what we mean. You have your y, your x-axis, okay? You know, this is positive y, negative y, then negative x, positive x. So if a vector is in 2 dimensions, simply the vector has its y and x value. That is the whole idea of a vector in 2 dimensions. So if maybe I have a vector here, say this is a vector. To locate the position of this vector, you are going to use its x-coordinates. The x-coordinate, which is, you know, the x value, you take it from the x position of this vector, look at it, dot, 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 dot. You've located the value, let us say x1. And then to the vertical axis, dot, 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 let's say y1. So you see, to locate the position of this vector in this Cartesian plane, or rectangular plane, your x and y axis, okay, that graphical representation of x and y axis is called Cartesian or rectangular plane, rectangular coordinates, rectangular coordinate system. Is that okay? Rectangular coordinates. So this representation, this vector is said to be in plane. I can connect the vector from the origin. I can connect the vector from what? The origin to this point. Now let me fix our arrowhead to show direction. You see this vector, it is in northeast direction. The vector is in what? Northeast direction. Now this vector has its y value. It also has its what? X value. That is why we say it is in 2 dimensions. Because this vector is between x and y. It is not purely x and it is not purely y. We say that the vector is in 2 dimensions. You can use the x and y coordinates to locate that vector. So whenever a vector is in 2 dimensions, that vector is said to be in plane. That is what you should take note of, plane. Vector in a plane. And when a vector is in a plane, it is represented on the Cartesian plane using Cartesian coordinate. The Cartesian coordinate is also called the rectangular coordinate or rectangular plane. I hope I'm communicating, right? Now that we have this, it becomes important for us to bring in certain laws of necessity that can be used to find the magnitude of this vector. Let me say that I label this vector as vector OP. Let this point be point P. How can you calculate the magnitude, the size, the value, the modulus, M-O-D-U-L-U-S? All these terms, they mean the same thing. This vector in 2 dimensions, how can you find the magnitude? How can you find the size? How can you find the modulus? How can you find the value? How can you find the length? Once again, all these things, these terms I said, or these words I use, they mean the same thing. So take note in case your examiner uses any one of them to ask you a question. So we're going to find out how you evaluate vectors in 2 dimensions. We've already treated that in 1 dimension. Are we ready? And it's also important for us to know how to get a direction. We're going to deal with how to get a direction as well too. So let us get to business. The first, and what I consider as the most important concept of resolving vectors in 2 dimensions is bringing in the concept of Pythagoras theorem or Pythagoras rule. Is that okay? Now, if you look at this shape, OPX1, this shape is a right angle triangle. So you see, from here to here, we can call it X. From the origin to this point, we can call it X. And then from the origin to this point, which is along this vertical, we can call it Y. We can call it what? Y. So we have X and we have Y. Now, the vector made this angle. Look at this angle, theta. Let's represent that angle as theta. Since the vector made this angle theta with the positive x-axis, take note, the angle of a vector by standard is always measured from positive x-axis anti-clockwise, this way. Anti-clockwise, or you can say counterclockwise, it means the same thing. So anytime you want to determine the direction of a vector, all you have to do is to calculate the value of the angle that the vector made with the positive x-axis, that is with the east cardinal point. You measure from that point and you start doing. Let us assume that the vector is here. Let's assume that the vector is here. You see, the direction is southwest. Usually, in terms of the angle which we use to determine the direction of a vector in 2 dimensions, we'll measure it from positive x-axis until it touches that vector. So that angle will give you the direction. Anyway, what I want you to observe here is that this shape, look at it from here to here to here, is a right angle triangle. It's a right angle triangle. And because it is a right angle triangle, we can bring in Pythagoras theorem. Please let me check once again the network situation. It's hanging here, okay? It has unfreezed me. It has unfreezed me. It's just, as always, so just freeze me and with time it will unfreeze. Or maybe at your end, the network may just be okay. I don't know. Let's move on. Through the camera, it's okay. And the camera network seems to be okay. So let us look at Pythagoras theorem on this. How do we determine the modulus OP? How do we get it? So to obtain OP using Pythagoras theorem, that's the first law we want to bring in here. Pythagoras law, rule, or theorem. Pythagoras rule. You need it whenever you are dealing with vectors in 2 dimensions. We want to calculate the magnitude of the vector. So imagine that two vectors, right? Now, imagine a vector is inclined between y and x-axis. Look at it, something like this. Something like this. So this is the vector. The vector is between the x and y axis. How do you determine the magnitude of this vector? Are you following? How do you get the magnitude of the vector? Because this vector, now if you look at it, has two components, the vertical component and the horizontal, because it is between them. It is not vertical, it is not horizontal, it has both values. So because this shape, if you close it here, you get a right angle triangle. Or if I go this way, right? If I go this way and then I drop a perpendicular height like this, this is a right angle triangle. For that reason, Pythagoras' theorem must play a crucial role here. So to get the magnitude OP from Pythagoras' theorem, OP squared, that line, that length OP, the square of it, which is the hypotenuse, you know that OP is the hypotenuse, it's going to be equal to x squared plus y squared. So that to get our OP, the length OP, the magnitude, which I can now write like this. In fact, let me place the magnitude of the length OP. The magnitude of the length OP. So I have something like this. Magnitude of this length OP is equal to square of this plus square of this. Okay, so to obtain our OP, that magnitude of that length OP, vector OP, it is now going to be equal to square root of x squared plus y squared. So this is the first formula I want to take note of from that rule, that Pythagoras rule. Normally, no examiner will ask you about Pythagoras rule when talking about vectors, because we do not consider Pythagoras rule, Pythagoras theorem, as a law of vector. We don't. When you're talking about laws of resolving two-dimensional vectors, usually we focus on parallelogram law and triangular law. We are coming to that. But I'm now telling you that, you see this parallelogram law, right? And then triangular law is actually a unique form of the extension of parallelogram law. Because if you draw a parallelogram now, a parallelogram is made up of two triangles. So triangular law is just like an extended form of a part of parallelogram law. But hey, calm down. You can see now that triangular law is linked to parallelogram. Like I said, a part of it. Now, parallelogram law is actually Pythagoras theorem extended. This is something that many scholars, many students may not know. Okay, let me just say some students. Some students may not know that parallelogram law is actually an extension of Pythagoras rule. But I'm going to show you today. I'm going to show you. The only thing is that parallelogram law is used for a triangle that is not right angle triangle. Parallelogram law is used for triangle. Pythagoras is used for triangle. The only difference is that for Pythagoras, the angle between the two vectors, like in this case, if I call this a vector, this horizontal is one vector, and then the vertical is another vector. And then you have to calculate the magnitude. The magnitude will be this line drawn. Don't worry, the magnitude is going to be the diagonal. We're going to state it under Pythagoras theorem. Not now, under parallelogram law of vector rather. Okay. So Pythagoras theorem is used when the two vectors meet at 90 degrees. Then parallelogram is used when the two vectors meet, usually at an acute angle. But if you use the knowledge of angles in mathematics, the acute angle can be translated or transformed into obtuse angle. You know, these things are things you should have good knowledge of from mathematics. Parallelogram law is used for acute angle or obtuse angle vectors, when vectors meet at acute angle or obtuse angle. Then Pythagoras is used specifically when two vectors meet at 90 degrees. So parallelogram is actually an extension of this guy. That is why this is our beginning point. The point of interest first, before we now move on to another way of obtaining or resolving vectors in two dimensions. So look at it. To get the magnitude of this OP, it is going to be the square of this horizontal plus the square of this vertical. Because of the way this angle is fixed, you see this side facing the angle. If you draw a line from here, dot, from the angle, it's going to touch this vertical. So this side is called the opposite. Whereas the horizontal side here, as it is called the adjacent, because the angle of the vector is not facing it. It's not. So we call it the adjacent. While where the side of the right angle triangle that the angle is facing is called the opposite. Then this length, the diagonal here, is called the hypotenuse. It's important for us to understand something here. Watch. You see this diagram? If I pull it out, it is just like two vectors meeting at an angle. Look at one of the vector OY. Let's say OY. Then the other vector from here goes this way, OX. So you have this vector, We represent this as Y, and then I call this X. So how can you now get the magnitude of these two vectors? These vectors is in two dimensions. You can see both of them are moving at different, they are moving in different directions. Both of them are moving in different what? Directions. But they meet at a point, having an angle. That is how we say they are vectors in two dimensions. They have two planes. One is the Y and then the other is the X. And then to get the magnitude, you resolve the diagonal. The diagonal is the hypotenuse of this guy. So if you drop this, you now get your right angle triangle. So that's just the whole idea. Which means that this OP has horizontal value X and the vertical value Y. I can actually call this OP subscript X. That is the vector, the component of this vector in the X direction. OP sub X. Here, look at this one. This is the main OP, the diagonal, the hypotenuse. Its horizontal value, I can call it as the component of this vector in the horizontal direction, OP sub X. And then look at this, I can represent it as OP subscript Y sub Y, which means the component of this vector in this direction. I hope you are following, right? Well, I've just told you that the starting point when you're studying vector to calculate the magnitude of vectors in two dimensions, the starting point is Pythagoras. Although no examiner will ask you to state Pythagoras' theorem on the vector, because we don't consider Pythagoras as a law of vector. We don't. But you need it because that's the starting point. Now, how do we determine the direction of this vector? How do we determine the direction? Please let me check the network situation. This is just busy hanging. Let me check. I hope the network is okay there. Gumok saying, what is your question? How can you have that vector going that way when the magnitude isn't there? I don't think I understand your question anyway. I don't think I understand your question. Hypotenuse, not hypotenuse. I don't know what you're saying, young man. I did not pronounce that anyway. Please let us move on. No time. Now, if you get the magnitude, this is the magnitude. Please, all these things, you have to define them in your notes. OP is the magnitude of the vector. This OP. This X you're seeing here is the value of OP in the x direction. Look at OP, its value in the x direction. Because I told you that this OP, since it is not purely vertical and it is not purely horizontal, it's between them. So it has two components, two values. Value in the vertical direction, value in the horizontal. So this x you are seeing is actually OP subscript x, which is the vector value, vector component of this OP in the x direction. And then this one is the vector component of this OP in the what? Y direction. Now, how can we determine the direction of this vector now? Because like I said, two vectors are acting in completely different direction. One is going this way, another one is going this way. I will now want to get the resultant of these two vectors. We say it is the diagonal drawn from the point of intersection. This is the resultant. Of course, we are going to state that under parallelogram law anyway. So something is just going this way. Another vector is going this way. Which direction will it take them to be? That is why we have to bring the resultant, which is the diagonal drawn from the point of intersection of the two vectors. So it is the direction of this diagonal, this resultant, that will now determine the direction of the two vectors going like this. Because you must take a single vector. Look at here, one is going vertically, that is northward. Another is going horizontally, that is eastward. Different direction entirely. So to get the direction of the two vectors put together, it is the direction of the resultant that we are going to use. Now, I have shown you how to get the magnitude of the vector, the resultant. I've shown you, look at Pythagoras theorem. So what about the direction theta? To get the direction theta, you have to bring in your basic trigonometric ratio or identity. Direction of the vector. Direction of the vector, this vector in two dimensions. Please take note. Direction of the vector in 2D. So it is just for you to determine the value of this angle. And how do you get this angle? Of course, it's not something you cram unnecessarily. You have to understand it from basic trigonometric identity or trig ratio. This is an angle theta. It has, in this right angle triangle, we have opposite, we have adjacent. So if you have angle theta, you have opposite, you have adjacent. Which trig identity, which trig ratio relates these three guys, these three quantity? The angle, the direction, the opposite, and the adjacent. Is it sine, cos, or tan? With good knowledge of trigonometry, which of course I will still teach you in our live class, even though I've done that part, past academic section, I will still show it here. It is tan that relate both of them. You use tan theta to be equal to the opposite, which is the vertical, OPX. Sorry, OPY, the y component of this vector, which I simply call y. Then all of OPZ, sorry, OPX rather, OPX, that is the horizontal component of this vector, which I just used x to represent. Now, to get the value of theta, which is the direction, theta is now equal to tan inverse or arctan. Tan inverse, you're taking the tan to the right-hand side. Y over x. That is tan inverse of the opposite over the adjacent. Here's my marker. I hope we are learning. See how calm I'm taking this. Vector is a fundamental aspect of sciences and engineering. If you even come to the aspect of computer science, coding, are you following right? All this software design stuff, there are things related to vectors, matrices. Are you following? Then calculus. So this is a topic you want to really give serious attention to. Now we've analyzed this. Let's call this equation 2. Let's call this equation 2. I think we are done with this concept. We're now going to move on to the laws of vectors. When we talk about these laws of vectors, these laws actually apply to vectors in 2 dimensions. I've shown you how you can deal with vectors in 2 dimensions. When the 2 vectors meet at an angle of 90 degrees, you use Pythagoras theorem. That is the starting point. In fact, as a matter of fact, before I move on, how about we solve a question on this quickly? Because I'm done analyzing where Pythagoras theorem came in. So I'll wipe this board, this part of the board, and then we shall take a question quickly before I introduce you into the laws of vectors. Before I introduce you into the laws of what? Vectors. Is that okay? Let us look at this question. So it's going to be question 1. Although usually I like treating this whole thing before we pick questions, okay? Let me show you something. So you know how to apply this. After that, before I move on to the laws of vectors, I would like us to see how we apply the knowledge of sine and cos to resolve some things here. A man walks 3 kilometers due. A man walks 3 kilometers due. I would have used due north and due east, but I don't want to do that. The reason why I don't want to give you due north and due east is because in that first quadrant, this first quadrant, both sine, cos, and tan, they are positive there, right? And of course, the angle, getting the angle is just purely acute. I would like to take this thing to southwest. A man walks 3 kilometers due west, and then 4 kilometers due south. Full stop. Calculate the resultant displacement. Calculate his resultant displacement. And direction. And the direction. Or let's say, and his direction. And his direction. Now, the direction of the man. I hope the network is okay at that end. You just keep hanging and hanging here. All right. Let us see how we solve this problem. It's a simple one. Nothing is there. Now, if you look at, if I said you should describe the man's motion, all right? The man walked west and then south. So the way you are facing me, let me turn this way. This is my west, and down is my south. So we can say the man walked this way and then this way. Which, if I represent it on the board, if I say this is the starting point, we could say the man walked this way, west, 3 kilometers. And then from here, south, 4 kilometers. So you could have this, and then to calculate the resultant displacement, that single vector, which acting alone will have the same effect in magnitude and in direction as these 2 vectors. You know, I defined resultant of a vector in our previous class. That was last week, Friday. You know, every Fridays, 8 o'clock or 8:30, I come on live to take you on physics. Every Monday, the same time, maths. And every Wednesday, the same time, chemistry. So we have a standard timetable that guides us. If you have not subscribed to this channel, please hit the subscription icon. Then go ahead, turn on the notification bell. After you subscribe, click on notification bell. Now a menu will pop up. You'll see all, personalized, and something else. Select all, so that anytime I come on live or I upload any video, you will be the first to be automatically notified. As a matter of fact, you will receive a notification 30 minutes to the time if I had already given the information out. But like today, I did not give the information out like that. What is happening? I don't know what is happening here. I hope this did not cut off. I hope it did not cut off. Which country gets you? I'm from Nigeria, all right? In a state called Anambra State, Oka to be precise. All right, I'm just trying to show you something. Generally, we don't sketch this thing like this. I'm just trying to like give you a, rough analysis of this. If you're sketching it, we use a proper Cartesian plane. Yes, don't worry, I'm going to show you. But even if you use this, it's not wrong anyway. It's not wrong. So from here, the resultant is the diagonal drawn from the point of intersection of these two vectors. I hope you're following right. And these two vectors, they meet at 90 degrees because from the question, one is pure west, the other one is pure north. North and west, sorry, pure west and pure south. West and south, they meet at 90 degrees. I hope you're following right. So from here, you draw this line and this represents the resultant. Then determine this represents the resultant displacement. Just calculate it. To do that, you drop your vertical. So you get a right angle triangle. This is the angle, theta, that the resultant made. But usually, like I said, to get a clearer picture of this, we use the Cartesian coordinate. We use the Cartesian coordinate. So I'm going to wipe this, even if one could solve the question using this diagram. But please, let's go back to the proper diagram we use. Our cardinal point. Cardinal point, this is north, south, east, and west. Okay, so you see that the man walked this way 3 kilometers. So I'm going to say this is 3 km. This is the origin. Let's say that this is the starting point. Are you following right? 3 kilometers. Then next, the man now walked 4 kilometers north. Is it north? The man walked 4 kilometers south. 4 kilometers south. So I'll come here. You notice that in the west direction, I placed an arrowhead there. In the south direction, I placed an arrowhead. I'm taking this to be 4 kilometers. Are you following right? Because I placed arrowhead because the man walked in that direction. So if you take the movements, the movement of the man as displacement is a vector quantity and you must show the direction. So I had to fix arrowhead here. I did not fix here. I did not fix it because there's no vector there. Are you getting me right? So you take note. There are some times you may meet something like this. Maybe something like this. So you have vector here, you have vector here, you have vector here, you have vector here. There is no vector here, there is no vector here. Wherever you have vector, an arrowhead is going to be drawn there. That's the standard. Now with this Cartesian plane, what I have to do now is draw from the point of intersection. You draw the diagonal. Okay? Now, this resultant made an angle theta here. Made an angle theta. The 3 kilometers, let me write it on top, please. 3 km. So if you drop your perpendicular height here, dot, this way, all right, you would see that you have your opposite. This is y, and then this is x. This is what? X. Are you following right? And so from here, you can calculate the resultant displacement. You can get the magnitude. You were asked to find the resultant displacement. It's still the same as determine the magnitude of the man's motion. All right? Applying Pythagoras theorem, because this is a right angle triangle. Look at your y. This is the value from here to here. Are you getting me right? Because the value you have along the vertical is what you transfer here. So we don't know this resultant. Let's call this R. We don't know it. So from Pythagoras theorem, the resultant is simply the square root of x squared plus y squared. So that the resultant vector is now equal to square root 3 squared plus 4 squared. And if you solve this, you are going to get 9 plus 16, which will give you square root of 25. And then the resultant will now be equal to 5 kilometers. So, although the man walked 3 kilometers west, 4 kilometers south, the overall motion of the man to where he got himself, to where he found himself, starting from the origin, from his starting point, this is where the man, let us say, okay, you have something like this, dot, 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 that the man is somewhere here now at this point. Are you following, right? He walked this way and then this way down. At this point, this is where the man is. The actual displacement of the man, which is distance covered in a specified direction from his starting point, is actually 5 kilometers. Is actually, if you were to go straight this way, instead of going like this and turning this way, moving this way, instead of doing, stressing himself that way, he had to go this way, can go directly like this and locate the point which he wishes to be. I hope the network is okay. They look at what is happening. This device I'm using to track it. It's just hanging. All right. We are moving on. If the network is disturbing at your end, you could just indicate. Andres, you've obtained 5 kilometers. That's correct. 5 kilometers. That's correct. And you say the direction is southwest. You say the direction is southwest. Good. But you see, sometimes your examiner will not expect you to give the direction using these cardinal points, this, that. They might want you to get the angle, because generally, this problem is just like bearing and distance. The direction is usually determined by the angle, because it is as if the man is at this point initially, and the man wants to come this direction. The man would have to turn. Okay, just imagine that I'm standing something like this. Maybe facing here. And then I want to go down west, south. How will I turn? To what extent will I turn to be able to move in that direction? So that angle is very important. Now we have gotten the magnitude of the man's displacement, the resultant. Let us now determine the angle. Remember, I told you that to get the angle, which tells us the direction, you use theta. For direction, comma, we're going to say that theta is equal to tan inverse of the opposite over the adjacent. So if you substitute into this formula, look at the opposite is 4 kilometers, 4, because the angle theta is facing it. So you have 4 all over, the adjacent is 3. Now evaluate the tan inverse of this quantity. You can reach out for your calculator, then shift tan 4 over 3. This gives 53.13. Let me just approximate to 53 degrees. So the direction theta is equal to 53 degrees, but you want to be careful at this point. That is why I decided to give you a question that defines west and south, or south and west. If you are to quote the angle that the man would turn so as to locate the direction he is to take, if you are to determine that angle, remember I told you that the angle of a vector is measured from positive x-axis. Yes, some examiners may leave this in the option and then quote it southwest. Some examiners may leave this thing in the option and then quote it southwest. But there is how you can also get it better. Because this value you are seeing here does not really tell you that, it doesn't tell you that the man is moving southwest or west of south. It doesn't. 53 degrees, if you come to this diagram, is in the first quadrant. 53 degrees in the first quadrant. Because you know, from east to north is 90. North to west, another 90, making it 180. West to south, another 90, making it 270. South to east, another 90, making it 360. Are you following, right? So if you calculate theta to be 53 degrees, 53 degrees will be in this quadrant, within this quadrant, the first quadrant. So what do we do to actually get the angle? To find out that this thing is actually southwest, not northeast, because the 53 degrees is northeast, east of north. Like I said, 53 is not here, it's not here, it's not here. So this 53 you calculated is actually the value of this angle theta, which is from the negative x-axis, from the west. Are you following, right? Some examiners in their option, they might leave that 53 degrees. But let me show you the correct thing that it could have been. Because usually, just like bearing is measured, bearing. If you've studied bearing before, you know that bearing is measured from the true north, anti-clockwise. Bearing is measured from this north, anti-clockwise. Don't worry, in our math class, we're going to treat that. Bearing, anti-clockwise from north. For vectors, vectors is measured. Bearing is clockwise, please. I'm sorry. Bearing is measured clockwise from the north. Bearing is measured clockwise like this from the north. Vectors, by standard, are measured anti-clockwise from the east. So for us to get the actual direction, angular value, we are going to take the angle from the positive x-axis this way, this way, this way, this way, until it touches the vector. So the direction of the vector is actually the value of the angle measured from this east, anti-clockwise, down to once it touches the resultant vector. You stop and then measure the angle. The question will now be, what is the actual value of the angle now? So it's simple. You have gotten theta to be 53. For us to know the quadrant where the cardinal point between which the man is moving towards or moving at, as the case might be, you have to measure it from the east. So coming this way, from east to west is 180. And then from west to where this resultant vector is 53. That's what we calculated. So if you measure from east, you can see that you measure from east this way down to west, it gives you 180, then add the 53 that you calculated in order to get the angle of the resultant. So I can say, therefore, direction of the resultant displacement. The direction of the resultant displacement is equal to 180 plus 53. If I solve 180 plus 53, this is going to give us 233 degrees. 233 degrees. Now, if I tell you to measure 233 degrees from the east, taking the east to be 0 degrees, of course, just like if you're talking about bearing from the true north and you measure clockwise, the north is assigned 0 degree. For vector, the east is assigned 0 degree. So from here, you move this way down to the west, you get 180. You are trying to locate 233. 233 will cross 180 to this west-south or southwest. It will cross the 180, but it can't get to the south because south is 270. Look at 233 will now be between west and south. And that is how you know that the man is actually moving west of south or southwest. This is the value of the angle that gives you the correct answer. Not actually this. But like I said, sometimes examiners could leave this for us. But again, you could also see this. In a case where you see both of them, please, in an option, maybe in a question like this, see both of them in an option. The correct answer is this. So let's conclude. The magnitude of the man, we are asked to find the resultant. The resultant and direction. The resultant and direction of the displacement. Is, the magnitude is 5 kilometers. 5 kilometers, then comma, 233 degrees west of north, west of south or southwest, west of south, or you can pronounce it southwest. This is how we solve this question. But instead of this 233, you could still fix 53 there. It's still okay. With this 233 degrees, I really don't need to even indicate west of, in fact, let me wipe it. I don't really need to even indicate west of south. I don't need it with this 233 because the 233 already indicates that direction perfectly for us. That is southwest. I've shown you if you measure from the east, 233 will be in the third quadrant, west of south or southwest. But if you are using 53 degrees, then you have to indicate that it is southwest. In fact, let me write or 5 kilometers. So I show you the various ways you present the result. 53 degrees, I think it's usually written south, 53 degrees west. Good. South, 53 degrees west. Or you can just simply write 53 degrees west of south or 53 degrees southwest. However you want to. So that is it. Either you go this way with the 233, no need of indicating southwest. But if you're using this 53, please, you must indicate the cardinal point for us. Because 53 ordinarily is not in this quadrant. 53 is in the first quadrant. So if you are using this angle, you must tell us that, hey, it is southwest too, according to your question. But with the 233, which is the most accurate value, you really don't need to tell us southwest. Somebody will know already that that value is southwest. All right. Let me check the network situation. Let's check the network situation, how far we've gone. We are 49 minutes gone. Please let me adjust the camera. I'm sorry that some parts were cut off. Please, when is mathematics? Mathematics, Imwetinian, Florence. Our mathematics class is on Mondays, 8 o'clock p.m. That is 8:30 Nigerian time. That's West African time, all right? Okay. What is the network situation over there? Remember, this is meant to be a 1 hour, 30 minute. All right, I'm sorry, the network went really down. A moment ago, I had to do everything I can to boost it. All right, so I think the network's a bit up now. Start boosting and boosting and boosting. Let me see. Okay, Chinedu, network is okay, all right. Let me see, I've tried boosting the network. Okay, I think I can continue. Now I want to look at laws of vectors. Laws of vector. There are two of the law we are going to deal with. Laws of vector. One, parallelogram law. Parallelogram law. Parallelogram law of vector. And then two, triangular law of vector. Triangular, parallelogram law, and I will state triangular law of vector. As much as possible, I would give you the formula for parallelogram law. For triangular law, there is no specific formula. The only thing is that once you're able to bring out the triangle, you can actually use certain, knowledge of sine rule, cosine rule to solve the problem on it. But most times, the triangular law of vector, when you are given problems on it, I think it's usually geometrical approach that's used to resolve that. Okay, so we want to look at parallelogram law of vector. Now, to deal with parallelogram law of vector, I'd like you to look at this. Imagine that this is the origin, and then you have a vector going this way. You have another vector going this way. Now, these two vectors, we assume that they represent the two sides of a parallelogram. These two vectors represent the two sides of a parallelogram, and that the vectors are represented in magnitude and in direction. Now, for us to get the resultant, what do? Just like I explained under Pythagoras. Remember, I told you that parallelogram law is simply an extension of Pythagoras' rule. For us to get the resultant, it is the diagonal drawn from the point of intersection. So all you have to do is to complete the parallelogram. So with what I've just said here, let us now state parallelogram law of vector. I'm going to wipe this. By the time we state it up to that point, I'll now draw it. It states that if the two sides of a parallelogram is represented with a vector in magnitude, or is represented with vectors in magnitude and in direction, the resultant is the diagonal drawn from the point of intersection of the two vectors. The other way around, we can state it this way. If two vectors are represented in magnitude and in direction by the two adjacent sides of a parallelogram. I take that again. If two vectors are represented in what? Magnitude and in direction by the two sides of a parallelogram, the resultant of the vector is the diagonal drawn from the point of intersection of the two vectors, represented in magnitude and in what? Direction. That is to say, the resultant is the diagonal you will draw from where these two vectors intersect. And that resultant, which is the diagonal that you're going to draw, will also be represented in magnitude and in what? Direction. Finally, when two vectors are represented in magnitude and in direction by the adjacent side of a parallelogram, the resultant of the vectors is the diagonal drawn from the point of intersection of the vectors, also represented in magnitude and in direction. So this is the resultant. Now all you have to do, if I call this vector, vector OA, and I call this one OB, all you have to do is to complete the vector. And how do you complete it? You go this way, just complete the parallelogram. Draw a line parallel to this one. So as I'm watching this, let me take a line parallel from here. Something of this kind. So you notice that this line, look at this line, all right? It is parallel to this one. You are going to use an arrowhead to represent the direction. Then again, come to the head here. Draw a line parallel to this one. It's going to go this way, something like this, parallel to this one. Of course, use your arrowhead as well too. Good. I've completed the parallelogram. These two vectors, they met at this point. So there is an angle here. Let's call the angle theta. Let's call the angle theta. That is the angle between the two vectors. Let's call it theta. Now this is a parallelogram. Let me call here point C. Let me call this point C. So OC is actually our resultant. Consider the resultant R is equal to the vector OC. This vector from here to here. That is the resultant. That is the diagonal, you know, drawn from the point of intersection of the two vectors. Now, I want you to observe something here in this diagram, okay? Because we are going to move to mathematics now. When dealing with shapes, what are certain properties of parallelogram? two opposite sides are parallel. Like in this case now, this line and this one, they are parallel, which means they are equal. Then this one and this one, they are equal also because they are parallel. You see, opposite angles are equal. The angle here and the angle here are equal. The angle here and the angle here are equal. Now, I want you to know the value of the angle at this point, this angle. This angle theta, which is where the two vectors intersected here, is acute, less than 90, as you're seeing it, less than 90. That's just the only difference between parallelogram law and Pythagoras theorem. Why Pythagoras theorem, these two vectors will meet at 90 degrees. For parallelogram, they don't meet at 90. They meet at an acute angle. Or otherwise, if you want to get this one, obtuse angle. What is the value of this angle? This angle you are seeing here is 180 degrees minus theta. Because, like I said, in terms of properties of parallelogram, opposite angles are equal. And then one of the other adjacent angle, because this angle is adjacent to this. This angle is opposite to this. This angle is adjacent to this one. It is also adjacent to this one. These two angles are opposite. These two opposite. These two opposite. But this one is adjacent to this. All right, that aside. If this angle is theta, this one will be 180 minus theta. It's a property of parallelogram. And that goes from the knowledge of geometry, where you talk about alternate angles, vertically opposite angles, corresponding angles. I don't think I have enough time to go into details. But look at dot, 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 dot. These two lines are parallel. Being that they are parallel, look at this line that went through is a transversal. This one, OA, is a transversal. Okay, and if you use that knowledge, you will find out that this angle will be 180 minus this one, using the knowledge of angles on a straight line. Okay, because this angle is going to be corresponding angle to one outside here. It's going to be corresponding to one outside. Like I said, I can't go into details in that now because it's not part of our work. Just know that this acute angle, if we call it theta, this one will be 180 minus theta. Also, this angle at point C will also be theta, because it's equal to this. The angle at point B is equal to 180 minus theta. Now that I've given you I've stated parallelogram law and then sketched it, I am going to now give you the formula of parallelogram law of vector used to calculate the value of the resultant. This resultant, I am calling it R. You can also call it OC. Now, this vector OA, let us call it A. Then this vector OB, let us call it B. Is that okay? So that in bringing out the formula, I will not use too many OC, OB, OA. I don't want you to be confused. Okay, so we go. The resultant, according to Pythagoras, we'll start from there. This thing is just like hypotenuse. This diagonal is just like hypotenuse. The only reason why we can't call it hypotenuse is that this triangle, like this shape now, look at OB and then OA. If you complete like this, you get a triangle. If I go this way, dot, 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 and then I complete that parallelogram like the way I did here, look at OAC is a triangle. So one can say, okay, let this be adjacent, let this be opposite. Automatically, this becomes what? Hypotenuse. But hey, you can't say that for this type of triangle because this thing is not right angle triangle. It's not. It is not. So here, the knowledge of cosine rule will be used. But I'm just still insisting and saying that all these rules you're saying, cosine rule is an extension of Pythagoras formula. Yes, that formula you know as cosine rule, which you use for other triangles that is not right angle triangle. So we go. The square of the resultant will be equal to the square of this A plus the square of this B. Now, the angle facing this resultant is this guy, 180 minus theta. 180 minus theta. If you are using this angle facing the resultant, please, this thing you are seeing is Pythagoras formula. Pythagoras. But because this diagram, like OAC or OBC, is no longer right angle triangle, it's no longer right angle triangle, it's another type of angle, of triangle. Either scaling triangle or isosceles triangle, as the case might be. Either scaling or isosceles. Or even equilateral. But it is not right angle triangle. That is why the formula cannot stop here. The formula stops here if these two vectors meet at 90 degrees. You bring in Pythagoras. But since these two vectors did not meet at 90, you would have to extend further the knowledge of Pythagoras. Now, if you are using this angle, this obtuse angle 180 minus theta, then here this guy is going to be minus 2 times this A, this vector A, times this vector B, then multiply by the cos of the angle facing this resultant. And the angle is 180 minus theta. But now watch. If you want to use this angle, this acute angle, the one we use here is obtuse angle. Obtuse. This angle here is usually in the second quadrant. This angle is usually in the second quadrant. That is why we are going with that minus. That's why we are using that minus, because this part of the formula you're seeing usually goes with positive sometimes. So let me write or. If you want to use the acute angle given from the question, because most times examiner gives you this acute angle, less than 90. This will be the formula. R square equal to A square, that is vector A square. Let me fix all these things so that you know we are talking about vectors. Vectors. So the square of the resultant vector equal to the square of vector A plus the square of vector B plus 2AB, then cos theta. Cos theta. So you want to take note of this, please. Note. Theta is acute. Theta is acute angle. So it is less than 90. Acute what? Angle. Then 180 minus theta is obtuse. That is greater than 90. So if I tell you that two vectors are inclined at, let's say, 135 degrees, this is the formula you are meant to use. You don't need to do 180 minus 135 anymore. You don't need to. Because 180 minus theta already gives you obtuse angle, and 135 is obtuse. This theta is acute. So you only do 180 minus theta if that theta is less than 90 given the question. Think of this now. If I give you theta to be 45 degrees, for example, that two vectors, they meet at 45 degrees. If you want to use this formula, you must do 180 minus that 45. But if you want to use this formula with this plus, this guy you are seeing here will simply be 45 acute angle. The whole idea is this. This sign is meant to be maintained as plus. If you solve with this obtuse angle now, for example, let's say in the case of that 135, which is the same as 180 minus 45 degrees. If you evaluate cos of an obtuse angle is angle that is already greater than 90. If you evaluate it, you're going to get a negative result. That minus will change this minus to plus, because you're going to have minus 2 times A times B times minus of that value of cos obtuse angle you got. All right. I think we are going to take a question on this. Let's take a question on this. Or before then, we talk about triangular law of vector. All right. Triangular law of vector, we'll state it, and then I'll take a question here quickly. After that, we close for today. All right. We'll meet next week for further calculation. Triangular law of vector. It states that if two vectors are represented by the sides of a triangle in magnitude and in direction, the vectors can be taken in order. The vectors can be what? Taken in order. So that is what triangular law of vector tells us. So usually if you are drawing the vector, like I said, we use geometric knowledge there. We don't use analytical method. Even this parallelogram, we can use a geometric method to sketch it, to draw it. And you draw to scale, you still get the same answer you get if they give you any question. You still get the same answer if you use geometric construction. You get the same answer as using analytic method. The formula method is analytical method. The formula method is what? Analytical method. So the same thing, if you talk about triangular law of vector, it is important for you to understand that that one, you can do it most times. Your examiner asks you that question when they want you to construct. When they want you to what? Construct. All right? So we have studied triangular law of vector when two vectors are represented by the two sides of a triangle, that the vectors, to obtain the resultant of the vector, you do that, right, by drawing a third vector that will close the first two vectors taken in order. I think I would like to write that law on the board. Let me write it for you. Triangular law of vector. It states that if two vectors are represented by two sides of a triangle, the resultant two sides of a triangle taken in order. You must take it in order. Two sides of a triangle taken in order. And then the resultant is a third vector. Is a third vector drawn opposite to the other side, or to the other vectors taken in order also. So that is what triangular law of vector states. And one could have something of this kind. Let us assume that I have a vector like this. From here, you have a vector from this point, go like this. Let's call this vector OA. Then you have another vector. You will draw it in order. You will take them in order. The second vector will go from this point, from the head here. This is the tail of the first vector. This is the head. So you go this way. So let us call this vector B. So you see, from tail, look at it, tail to head, vector OA. Tail to head, vector AB. Now to get the resultant is a third vector drawn, taken in order also, but opposite to the other two vectors. That third vector is drawn to close the first two vectors, something like this. It is drawn to close the first two vectors. So this is the third vector. Now, if you are to sketch this, usually you use your compass to measure the angle given you so that you know where to step this one up. Because they'll always tell you the angles at which the two vectors met. If maybe this vector and that is vector OA and vector B, if they meet at 30 degrees, when you draw this vector OA, to draw this B, you use your compass. Is it compass or protractor rather? You use protractor to measure 30 degrees up. If you measure 30 degrees away, that will now help you to know where you will draw this line through. Don't worry, we are going to have a special class when I teach the construction rather, of triangular law of vector and parallelogram law of vector. For now, we are looking at the analytic method. We are looking at the what? Analytic method. That's by calculation. And from here, to solve question on this triangular law of vector, to do the calculation, apart from geometrical approach where you construct. If you want to do the calculation, you just use your concept of sine rule and cosine rule to solve them. Sine rule and what? Cosine rule. You use it to solve them. But don't worry, we are coming to that. Let us just pick a question on parallelogram laws. We close today's class. Are you following, right? So we close today's class. We want to solve a question on parallelogram law of vector. Don't forget what I told you about the mathematical sign, when to use plus and when to use minus in parallelogram law of vector. Okay, depending on the angle given to you. If the angle is acute angle, that's side of 2AB. Before it, you have plus. If the angle given to you is obtuse angle, obtuse, which is already greater than 90 degrees, but less than 180. That side of 2AB, before the 2AB, you fix minus there. So we have this question here. We have this question, it's given this way. This is question 2 as we conclude. Question 2. By the way, let me see what the time is. This is 1:17. So we are almost getting close to our time. So we have this question. Two vectors are inclined at an angle of 45 degrees. Two vectors are inclined at an angle of 45 degrees. Calculate the resultant and direction. Calculate the resultant and what? Its direction. So the two vectors, they are inclined at an angle of 45 degrees. So it's something of this kind. Can make a sketch. I didn't mention the values of the vectors, please. Two vectors, okay, the values here, two vectors, 4 units and 3 units. Two vectors, 4 units and 3 units are inclined at an angle of 45 degrees. Two vectors, 4 units and 3 units are inclined at an angle of 45 degrees. Calculate the resultant and direction. Calculate the resultant and direction of the vector. So I can say that this should represent the 3-unit vector from the origin. Let's call this vector OA, and then let the other one be 4 units. Okay, they are inclined at 45 degrees, not 90. So even if you choose to use the approach of your Cartesian plane, all right, you know that this is 90. 45 goes this way. So you have one of the vector like this, and you have the other vector this way. So this is 45 degrees. The two vectors meet like this. This is one of it, this is the other one. Because these two vectors are not at 90 degrees to each other. They are not at 90 degrees. They are not. You cannot use Pythagoras theorem to solve it. Rather, you use what? You use your parallelogram law of vector. All you have to do from this point of intersection, take your diagonal, complete your parallelogram, and then solve. But anyway, let's go straight. No need of going back to the Cartesian stuff. So the resultant is this diagonal, and then I can complete my parallelogram, which is line drawn parallel to the other vectors. Here now, draw a line parallel to this vector, which should go this way. So this is my resultant R, I don't know. Okay? So the two vectors, they met at an angle of 45 degrees. So this is 45 degrees. Now you are asked to find the direction of the resultant. The direction of the resultant is this angle here. Let me call this angle alpha. Let me call this angle alpha. That's the direction of the resultant. Now look at this angle here. This angle will be 135, which is 180 minus 45. And 180 minus 45 will give you what? 135. So let me show it here. 135 degrees. 135 degrees. You see, this angle 135 is obtuse. It's obtuse because it is greater than 90. So you see, you have these two angles, but this is the one that was given to you in the question, that 45 degrees, which is the angle between these two vectors, OA and OB. Remember, this vector alpha is just from the resultant to the second vector B. And that is the direction. So we have to find a way to calculate that alpha at the end of getting our resultant. So let us conclude, please. There's nothing that is here. Let us take this vector as vector A. Let's take this one as vector B. Then you now use your R squared equal to A squared plus B squared. Now, when you come to this 2AB part, it is now your choice whether you want to use plus 2AB cos or minus 2AB cos. Now, if you are using plus 2AB, it is this 45 degrees that you're going to use. If you're using plus, then the cos, the angle that the cos will be bearing, will be carrying, will be the acute angle. But if you're using minus, the angle that the cos will be bearing will be 135, which is 180 minus this acute angle. Take note of that. Since they gave us acute angle directly from the question, why stress myself? Plus 2AB and then cos of that angle 45. Let's say cos O. If I were to use this cos B, then I would have talked about using minus here. So cos of this angle O. Please, this is not 0. This is angle O because this point is O. I can now substitute. To calculate the resultant, our A is 3 units is square root, B is 4 units is square root plus 2 times 3 times 4, then cos angle O is 45 degrees. Or any one of them you do, you get the same result. Or you could go this way. Please don't do this all stuff. Don't. If you start solving from here, just simplify. I'm just trying to show you that alternatively, you could use the obtuse angle, which will now mean that you're going to use minus here. Minus 2 times 3 times 4 cos open bracket 180 minus 45 degrees. And then if you use this one, you're going to get 135. Cos 135 will give you a negative result. That negative result will multiply this negative to change to plus. Cos 135, which you get here, will be equal to cos 45. But one of it will be positive, the other will be negative. Let me just show you quickly. Cos 45. Cos 45 is 1 over root 2. But let us see. Right? Cos 45, that is root 2 over 2 from what it is given to me here. And that root 2 over 2 is the same as 1 over root 2. If you rationalize, you get root 2 over 2. Get it in decimal points. The decimal is 0.7071. You can see for the 0.7071 cos 45. If you solve cos 145, take 135. Take note, this one of 45 gave us positive. 135 will give us this same 0.7071, but negative of it, because 135 is in the second quadrant, and in the second quadrant, cosine value there is negative. Let's evaluate it and see. Cos 135, you have your calculator there, you can actually follow along. So you see, minus root 2 over 2, which is the same as minus 1 over root 2. If you do sort rationalization, you get minus root 2 over 2. Let's obtain it in decimal. This is minus 0.7071. So if cos 135, this one gives minus, this is going to be minus 2 times 3 times 4 times minus 0.771, which automatically will change it into plus, giving you back this same thing. All right, let's start. Let me just focus on this. Forget about this one. I think I can wipe it now. No need. Or should I? I'll still leave it. I'll leave it. At least you were here in the class. You heard me as I explained this concept. So I think it's sufficient. Let's continue from this. R square will now be equal to 3 square will give you 9. This square, this is 9 plus 16. And now we have plus, let's evaluate cos 45, which we've done. This times this is going to give us 24, then times 0.7071. Please, I don't have enough time, so let us round it off once. How do you solve this? Add this and this, you get 25. Multiply this by this. So I'm going to have 24 times 0.7071. Whatever you get from this product, which is 16.9704, add it to 16, add it to 9, which is add to 25. If you add to 25, you get 41.97. All these things is 41.9704. So you can now take the square root of 41.9704 will give us that the resultant is equal to square root of what we obtained. 6.47 watt, so 6.5 approximately. I'm going to put unit, 6.5 units, 6.5 units. So that's the resultant of these two vectors inclined at 45 degrees. Okay, do they teach government literature and CRS here? No. This channel is for science students, please. So we are done with this. The next thing now is for us to obtain this value, the direction. How do we get the direction? Let me conclude it by wiping this part, writing it here. How do we get the direction? To obtain the direction, you calculate your alpha. And to calculate your alpha, you have to bring out this triangle. Permit me to label this point as point C. So this is the magnitude of the resultant vector. Now, to get the direction of the resultant, direction of the resultant. You know, because the two vectors are no longer at right angle. They are not at 90 degrees to each other. Rather, they are at 45 degrees. Because they are not at 90 degrees to each other, you cannot use tan inverse or vertical over horizontal. You can't. Which one is vertical here? Which one is horizontal here? You see? So you bring in another knowledge, a mathematical knowledge of trigonometry. So you're going to use sine rule. Direction of the resultant. Consider, let me say, to obtain direction of the resultant, consider triangle OBC. Triangle OBC. Consider triangle OBC. So we have an angle at point B here. If you consider it now, see, you know OB. Let me write it. OB, line OB of vector OB, which is equal to vector B. The value is 4 units. We know that. Then vector BC. Vector BC is equal to vector OA because they are parallel. They are what? Parallel. You can see both of them. Hence, they are equal. Which means that BC, which is part of this triangle we are considering, BC is also equal to OA. So BC, vector BC is equal to vector A, and the value is 3 units. So we know this value, we know this value. Angle OBC, which is the angle at point B, angle OBC is equal to 135 degrees. 180 minus 45. You need good knowledge of your trigonometry here. Okay, you need good knowledge of your trigonometry. Very important. Sine rule and cosine rule. Take note. This formula we used here for resultant is cosine rule. So with this, we can actually, we know the resultant here. We have obtained OC. Line O, vector OC is our resultant, and we got it to be 6.5 units. 6.5 units. It implies that, hence, by sine rule, because these values, the values we have for this triangle satisfy sine rule. We're going to have sine of this angle B, sine of angle B divided by the side facing angle B, sine rule. Sine of this angle all over the side, the resultant facing it, resultant vector. will be equal to, we are looking for this angle. So it's going to be equal to sine of this direction alpha all over. To obtain the direction alpha, let me indicate that it is alpha of the resultant. Okay, so it's going to be equal to sine alpha all over the side of triangle OBC, the side facing that angle alpha. You know, the whole idea of sine rule is this: sine of a particular angle divided by the side of the triangle facing that angle. That is just the whole idea of sine rule. So sine B over this resultant facing it will be equal to sine alpha, the direction, divided by this side, which is 3 units facing it. So it's going to be over BC, and our BC is equal to A. I've said that already. BC is equal to vector A. We can now substitute. Sine B is sine 135. Sine 135 divided by the resultant is 6.5. That's going to be equal to sine alpha, we don't know, and the value of vector A, which is equal to BC, is 3. Making sine alpha subject to the formula is going to be 3 times sine 135 divided by 6.5. Cross multiply, divide both sides by the coefficient of sine alpha, which is 6.5 here if you cross multiply. Now let us evaluate this. Sine alpha is going to be equal to, so we have 3 times sine 135. 3 times sine 135 gave us 2.1213. This calculator usually gives the result in short form first, but I usually convert to decimal. Now, the numerator here is 2.1213. I'm going to divide it by 6.5. So this is 0.3264, approximately 0.3264. Therefore, to obtain the direction alpha is going to be sine inverse or arc sine 0.3264. Sine inverse of 0.3264 or arc sine. Sine inverse is the same as arc sine. Cos inverse arc cos. Tan inverse arc tan. So the direction alpha. Therefore, direction, which is our alpha, is equal to, let's find out how many degrees. So sine inverse, shift sine, you invoke your sine inverse, 0.3264 gave 19.05 degrees, which is approximately 19 degrees. 19 what? Degrees. And that is the direction of the resultant answer. So we are done with the concept of parallelogram law, vectors in 2 dimensions. This is just one part of vectors in 2 dimensions. We still have a lot, a lot to deal with under vectors in 2 dimensions. We just covered a part of it. Triangular law of vector, most times students are not being introduced or are not being given problems on it like that. But like I said, we are still going to solve question on it. In our next class, we're going to solve question on it. But you observe that I'm using analytical method, calculation method to solve problems on them. If you are sitting for a theoretical exam, your examiner can ask you to use geometrical method, that is construction, to get their value. You construct to scale. That's what I'm going to establish, as in hold a special class for that. In fact, I will sit down. I won't stand on the board because I need my math set, protractor, compass, ruler. I need those to be able to do that. I'm going to use A4 paper, all right, plain paper, to show you how you can construct geometrically to get the same result. Okay, if not exactly the same, it will be approximately the same. But calculation method, which is this analytical method, is usually more correct than geometric method, construction method. Because while constructing, you might make 1 or 2 mistakes in your scaling and other things. Okay, for triangular method, majorly when questions are given on that, it is construction method that examiners might usually ask you questions on, which means it will come from theory part. Okay, in objective questions, you hardly are given problems like that. But if you're given any question on that, it's simple for you to calculate, for you to use analytical method. On triangular law, it's still simple. Nothing is there. You have your laws, your sine rule, your cosine rule, and that's sufficient. Okay. All right, so we are done with our class today successfully, and we thank our God and helper Jehovah for that. I hope you've learned something wonderfully well. We've just covered a part of two-dimensional vector. Remember, we also have a further math aspect of it, and we are going to cover all of them. In our next class, that is next physics class, next week, Friday, we are going to be looking at vectors in two dimensions. I'll still take you back to Pythagoras. Okay, now what we are going to do there, remember the Pythagoras question we solved today was that in which you were given a vector vertical and a vector horizontal, and then you were asked to find the resultant. You are asked to find the resultant. So you know R, you know RY value, you know RX value. You are not asked to find the resultant and the direction. Now, what if you don't, here you knew this one, and then we now calculated this one, the resultant, the diagonal. What if you are given this? You don't know this, question mark. You don't know this, question mark, but you know the resultant. Here, we didn't know the resultant. So the one we solved in our class today is something like this, under Pythagoras. You know the component of the two vectors, perpendicular vectors, vertical and horizontal, meeting at 90. You do not know the resultant. You do not know the resultant. So we use Pythagoras to solve it. Now, in our next class, I'll introduce you to the kind of problems whereby you'll be given the resultant value. Like the one we solved that we got the resultant. I think the resultant was 5 kilometers. Okay, and then the direction, 53 degrees or 233 degrees or so, southwest. What if you're now given just the resultant value? Look at this one, you know it, but you don't know the components. You don't know the vertical, the horizontal value of this. What would you do? Such type of, that idea can be used to solve problems like, I can tell you that a nail is fixed to a wall. A rope is tied to the nail. All right, a rope is tied to the nail, and the rope is at a certain angle. Are you following? What force will be required to pull the nail from the wall? In that case, you are pulling horizontally. Yeah, but then I give you the value, maybe the magnitude that you're using here and the angle that the rope makes. So the tension that you need, the force to pull it out, what could you do? And next class, next week, Friday, physics class, I'm going to be teaching you that, where you use resultant to obtain component of vectors, all right, in two dimensions. For now, make do with what you've learned under Pythagoras, what you've learned under parallelogram, law of vector. Do not forget that I told you that when two vectors are at 90 degrees to each other, to get the resultant, use Pythagoras rule. Also, remember that in our class today, I have also taught you that the direction of vectors in two dimensions is obtained using tan inverse of the opposite over what they are adjacent. Don't forget also that I told you, as you've learned, we've learned today that parallelogram law of vector is actually a kind of extension of Pythagoras theorem. We learned that you use parallelogram law of vector when two vectors meet at acute angle or at what? Obtuse angle. No longer at right angle. So that extends from Pythagoras into parallelogram law of vector. And we also learned that in parallelogram law of vector, you can use the acute angle value, where in that case, this sign will be plus before the 2AB. Or you can use the obtuse angle value. And how do you know the obtuse angle value? Obtuse angle will be greater than 90. If we had been told in this question that the two vectors met at 135 degrees, we wouldn't bother ourselves doing 180. You don't do 180 minus 135 to maintain this minus. Whenever you're using this minus, then if you are giving 135, for example, no need of doing 180 minus 135. Just fix the 135 directly because it is obtuse. Then you maintain this what? Minus. But whereby you are using an acute angle, if they give you acute angle, and the formula you remember is this one with minus. Remember that this will be 180 minus that acute angle. So we learned that concept so that we will be careful when solving questions on this. And then we went further to determine the direction of two vectors that meet either at an acute angle or at an obtuse angle, where we use parallelogram law of vector, you know. We have to determine the direction of the resultant. And to get the direction of the resultant, you use what? Sine rule. You can see that I showed you how to use sine rule to solve that problem. Then don't forget that we also learned about triangular law of vector. And I told you, in our next class, we'll also deal with that. I will organize a special class where I teach you how you construct in that case. If you are given questions to solve analytically on that triangular law, you use either sine or cosine rule depending on the values given to you. I'll be seeing you next week in our live class. But take note, before our live class, I can upload any pre-recorded video anytime. So if you have not subscribed, please subscribe now, like now as I'm saying it. After I subscribe, please click on the notification bell and then select all. So that if I happen to upload any video before coming live on Monday for our math class, you will be notified. Because of course, I might upload any video, on what we've done so far this week. Could be on math, on physics, on chemistry. So stay tuned always to this channel as GMAETS 41 continues to deliver top-notch academic work that you need. Share our videos to your friends. Invite them to subscribe to this channel. Are you following right? Encourage them. Good night, and we'll be meeting in our live class next week. On Monday by 8 p.m. for maths. Bye.